All right. Okay, well, it is Wednesday. Week 1 Wednesday is what this is. All right. Okay, so first a bit of just a little schedule change, okay? So this Friday, I'm going to be off doing something, so I'm not going to teach class on Friday, okay? But instead, I will teach the lecture that I had planned for Friday. I'm going to just do it tomorrow, okay? And I'm going to just do it tomorrow over Zoom at 9:30 a.m., okay? If you can come, and if you can't, I'll record the video and I'll post that, so it should be okay, I hope, all right? So my apologies, won't be here on Friday, but I will do the lesson, and it'll just be at Zoom at 9:30 a.m., okay? Now, one thing you have to be careful about, okay, is that normally, as far as the view quizzes go, oh, did I turn on today's view quiz? Let me just double check. Today's view quiz has been posted. Okay, so normally I only have one view quiz unlocked at a time, just so to prevent students from making mistakes and stuff. But there will be 2 quizzes because I'm doing the lecture early. There's going to be 2 quizzes open at the same time. So just be careful. Please double check which quiz you're answering when you enter your answers, because that'd be unfortunate if you watch the lecture but you enter the answers in the wrong thing, So anyway, that's what's going to happen. Okay. Anyway, that's that. Let's all right, so let's get into today's topic, and today's topic is I've titled Models and Machine Learning, and this is just kind of, I want to introduce kind of the framework and the setup of basically a lot of the ideas and things that I'll be introducing this quarter. And so this is what Wikipedia says is machine learning. It says machine learning is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without using explicit instructions, relying on patterns and inference instead. And it's okay, I guess. It's not a bad definition. It's just, sometimes Wikipedia has this tendency to write these really long, they string a lot of things together, and it takes a while to parse them out, right? So this is kind of what I've said is our big idea is that, effectively we try to fit models to data, right? And, as far as machine learning goes, people still have to make a lot of decisions regarding how we specify the model, but a lot of the decisions are going to be guided by the data and along with kind of algorithms. Algorithms just is basically a set of rules that we have to help us make decisions. And the decisions made by the algorithm is the, quote, machine learning part, right? So the machine is apparently learning or something. And I'm assuming you all took 101A for linear regression, and at the end you learned some algorithms to help you select which variables to include in a model, right? You had backwards stepwise selection. Is that what we call it? I don't remember, right? You start off with all the variables, and then you look at the table and it says these ones are significant and these ones aren't, and you start eliminating them one by one, and when you eliminate them, that changes things. That's basically an algorithm. It's basically kind of a set of rules that you have that you follow to help you make decisions, okay? Now, technically, you could give those same instructions to a robot, okay? And they could just kind of follow through the process. And the idea being, with you being a human with some knowledge, right? So being blindly led by an algorithm, being blindly led by some rules, isn't exactly always going to be the best scenario, right? So if you follow this, you might end up picking some variables. But as a human, if you had that subject matter expertise and you say, you know what, I'd prefer to use this variable over this other variable because blah, 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 blah. And And you could do that even if the algorithm says, you should pick this variable. Okay, you might have human reasons for wanting to choose something else, right? And it could just be as simple as like, people prefer this thing over this other thing, right? Like if you wanted to talk about how big a house is, you might say it's better to use the number of bedrooms than the number of bathrooms, okay? As far as like, you wouldn't say, hey, let's go check out that 3-bathroom house over there. It sounds a little more reasonable to talk about a 4-bedroom house or, something about the bedrooms versus the bathrooms. But, the algorithm might say, hey, the bathrooms, that's the thing. Okay, so anyway, there's a lot of this stuff about fitting a model and, statistical models. And so what exactly is a model? And it took me, so my undergraduate education was in engineering and was not in statistics. And so when I came to grad school and I said, hey, I want to study statistics, it took me a little while to feel comfortable with the concept of a model. Everybody was talking about models and statistical models, this and that. And I was like, I was always it felt like one of those questions where you didn't want to ask, what is a model exactly? But I wasn't quite sure. And so I don't know if you feel like, I'm actually not 100% sure what a model is or what we mean by a model. Like, I think I know, but okay. So this is my take on what a model is, right? So this is a model airplane. And basically the idea, when we talk about a model, we're saying this is a simplified representation of something complicated, right? So you have, an actual fighter aircraft is this very, very complicated piece of machinery, millions of dollars. And here's just like a simplified version of it that kind of represents what the thing is. And basically a statistical model is something similar in that it is a simplified representation of a real-world process that generates data. So if you think about, one of the data sets that we're going to be looking at, this data set, I'm jumping ahead here, this is the winning time of the men's 100-meter Olympic, what do you call it, 100-meter dash, where they're running on feet, okay? We Usain Bolt and things like that, just running, and this is the winning time, gold medal time versus the year the Olympics were held. Okay, now what are the factors that go into what is the winning race time? There's a whole bunch of things, right? It could be how hard the people trained, who was competing that year, the air temperature, was there any wind at all, the track material, the technology gains in shoes and stuff. It's all kinds of stuff, and it comes down to just a bunch of things going into this time. But we could just say, hey, you know what? A very, very simplified idea to kind of explain the times we see is we can just say, overall, as time has gone by, the winning race times have gotten faster. Okay, and so that's just a very, very, very simplified version of this data that we're seeing. What is the process that generates it? It's very complicated. All sorts of factors going into play. All we can just say, we can simplify this and just say, hey, you know what? As time has gone on, it looks like people have gotten faster, okay? And that's basically what we're trying to do, right? The process that generates data in the real world is complicated. There's usually many variables, many things ultimately determining the outcome, and statistical models, a simplified version of the relationships between variables in the real world. Usually it includes only just a small subset of the variables related to the outcome, and there's always going to be some leftover error term to account for everything else, right? Because when you simplify things, it's not going to be able to explain everything, and so you always have an error term to explain everything else. This quote from George Box, all models are wrong, but some are useful. And the idea there is you'll never get a model that exactly represents 100% what's happening in the real world, at least for anything that's a non-trivial situation. And overall, I say, the primary uses for statistical models is one is we can use them to make predictions, accurate predictions, and the other is we could try to use the models to gain an understanding of the relationships between variables. All right? And a lot of times we have to choose which of these objectives are more important over the other. So some models, such as neural networks and things like that, are going to be really good at making accurate predictions, but they do not help you at all to understand the relationships between variables. Okay? Other models like linear regression do a pretty good job of making predictions, but there's usually other models that are better at being even more accurate for predictions. But linear models are usually simple enough for us to understand kind of the relationships between the variables. And so, which model do you want to use often comes down to which of these goals and objectives are a little bit more important to you. Okay, so here again, the example we're looking at is we've got this 100-meter race, and we're looking at the track and field winning time. A bunch of things ultimately factor into winning time. In our simple model is we're going to just say race times have gotten faster over time, okay? And so if we know the year of the Olympic Games, we can kind of predict the winning race time. And basically a linear model, meaning we're going to just draw a straight line because we only have these two variables, implies that the amount that where we adjust our prediction remains constant through time, right? So if we predict the time improves by 0.05 going from 1920 to 1924, so over that 4-year span, if we're saying the race time improves by 0.05, we're also going to predict that the time improves by the same amount, 0.05, if we go from 2000 to 2004. Okay, that's basically what linear means. It means if the change is 5/100ths of a second basically between two Olympic Games, then it's going to be 5/100ths of a second between any other two Olympic Games type of thing, any two, 4-year span. Obviously, this cannot continue forever because it would say by the year 2600, we're going to be winning negative race times or something like that. So obviously, this trend can't continue forever, but maybe perhaps in the 80, 100 years of our data set, this trend holds, okay? But this is still, useful for the data that we have, okay? So as far as a linear model, we're going to fit a straight line, and that means to specify the model, we need to estimate two parameters, the slope and the intercept. And so when we talk about fitting a model is the process of estimating the model parameters, okay? I'm starting off with linear regression because I'm assuming everybody's already very familiar with linear regression. And so when I describe the process of how, these terms of fitting a model, specifying a model, and all of that, it's going to be in a context that you're already familiar with. And then, we'll just abstract this to different kinds of models, okay? And so basically, we want to estimate the slope and intercept so that the resulting model does the best job of fitting the data, right? And this is already a solved problem. We already know what the slope and what the intercept and all of that should be. But we're going to kind of approach this from a modeling perspective. And while I do that, let me go ahead and give you your first view quiz answer for today. The Wednesday, the first view quiz answer is E. E as in elephant, E. E as in elephant is your first view quiz answer, E. Okay, so this is what we want to do. We want to fit a model to our data, and we want the best parameter estimates, okay? Now, how we define what best actually is very important, and it determines what our objective function is, okay? So we're going to have a function. This is called our objective function that basically gives us a number for how well we are doing towards whatever our goal is. Okay, this is our objective function, and this is how we decide what is best. And so when we talk about least squares regression, best is the model that minimizes the total squares of the residuals, right? And so, you have the residuals, the actual value, and the predicted value, and there's a, let me, where did it go? The idea being, if this is the prediction line, this line, and here's the actual data value, the difference between this data value and the predicted line is your residual, and then we square that residual, and this corresponds to, these, and this brown square has quite a large residual, and squared residual is big. This purple dot is very close to the line, so it has a very small residual, and when you square it, it's quite small. And if I were to, say, shift the line further down, okay? So I could shift the line down, and so now the line is very close to the dot, so there's a very small residual here, and the brown square is quite small, but now, because I've shifted it down towards the brown dot, the residual between the purple dot and the line is much bigger, and when we square it, it gets bigger, and it's made it even worse for the orange dots and things like that, right? And so basically we're trying to figure out what is the best intercept, which shifts the line up and down, and that's going to change the size of the squares, and we're trying to figure out what is our best slope to minimize the total sum of squares. Okay, and again, you guys are familiar with this concept. And so what we have done is we've defined the objective function. The objective function is our residual sum of squares, and that is we take the difference between the actual value and the predicted value, and we square that difference, and we sum them up for all of the data points. Okay, and so this is the function that defines how well our model is doing. And so we also call it a loss function. We call it a cost function. These are things we're trying to minimize. We're trying to minimize our costs, or we're trying to minimize our losses, or things like this, right? So this is the function that we are trying to minimize. This is our objective function. And basically, when we do machine learning, and that includes linear regression, we fit parameters by trying to minimize or maximize some kind of objective function. And so a lot of our machine learning problems can be framed as optimization problems. We're trying to find the minimum or maximum of some kind of function. We have a function that defines how well we are doing, and we either want to minimize that thing or maximize that thing, and we're going to do that, okay? So even though linear regression is review, it does count at a very core, like as a machine learning model, because we could say, the way we pick the slope and the intercept is determined by kind of our the algorithm and the rules. Okay, we have a textbook in the class, and you do need it. And unfortunately, this textbook, I couldn't find a textbook that I was satisfied with that was free, and so this textbook you do have to kind of obtain. You have to buy it or something. So anyway, we're going to try to match the textbook's notation, okay? And so the actual values of the data are denoted as T sub n, okay? T, I think, kind of like the target value that we are trying to hit, okay? Versus the, traditionally we call this Y for our actual value. And then when we predict a value, all right, traditionally we would just call it Y hat as our predicted value. Now we're going to say, the value is going to be the result of a function where we plug in kind of our value x of n, and we've got parameters, the slope and the intercept. The slope and the intercept being w1 and w0. And so the result of our prediction is going to be the result of this function, okay? And so we're going to replace y hat with the output of the function with parameters w0 and w1 and our target. And so these two things are going to be equivalent. And rather than using the total sum of squares, we're going to have the mean squared error. So basically, we sum them up, and then we divide by n. Basically, we're just scaling the total sum of squared error, total squared error by 1 over n. And so basically, any function that minimizes the mean squared error is also the same answer that minimizes the RSS. Okay, so our loss function is going to be this. All right, so this is just a small change in notation, but I hope this is okay, that we're going to now use Tn and then f of xn with parameters w0 and w1. Okay, so a very common loss function that people optimize is the root mean squared error, RMSE, and you'll often see this thing popping up. And basically all we're doing is we're taking the square root of the mean squared error, okay? And basically, you know, because the square root function is monotonic, any value that minimizes the RMSE is also the value that minimizes the mean squared error, and so that's what we have there, okay? Because, you know, if a is greater than b, then the square root of a is going to be greater than the square root of b for all values a and b greater than 0. So that's what we have. Okay, that side note. All right. So basically, we have two parameters: the slope and the intercept. The intercept is w0. The slope is w1. And this function, it's a simple function, but we get it just by plugging that in. We're going to get the intercept plus the slope times x of n. And if we plug this into the loss function, now we're going to replace this function with w0 plus w1 xn. And we want to find the values of w0 and w1 that will minimize the total or the mean squared error here, right? And so we could do this with calculus, all right? And this would be kind of this is how we would do it. So we'd say, and if we're doing this, we treat the observed data, that is the x values and the target values in the actual data. Those are treated as fixed, and the loss function is determined entirely. Once you treat your data as fixed, your loss function is the value of the loss function is determined entirely by what your slope and your intercept are, okay? So, you know, kind of like in this thing, we're treating these dots as fixed, and really the total sum of squares here, or the mean squares, is determined entirely by what I choose for my intercept and what I choose for my slope, okay? Nothing else really comes into play as far as how big these squares are, all right? And so this is what we want, and that is we want to find the solutions to our problem will be the values of w0 and w1 that minimize this entire function over here, right? So this is our loss function. We're trying to minimize this. We want to find the w0, the slope, and the intercept that are going to minimize this, and that's going to be our solutions. w0 hat and w1 hat are the values of w0 and w1 that minimize this, okay? So we can try expanding this, right? So Tn minus all of this squared, and you just have to take my word for it as far as the algebra goes, that when you expand it, you get this, right? And then if you're doing calculus, you know, what part is this? Is this 32A? Okay, right? So, you know, Throwback Thursday. We look at this and we just say, okay, we'll take partial derivatives with respect to w0, partial derivative with respect to w1. You set those equal to 0, you solve, and you can get your solution there, okay? And so if you did that, here's your partial derivative with respect to w1, your partial derivative with respect to w0, and I'm not going to bother with the work. You'll just say, yes, I believe you, okay? And then, I mean, you can double check yourself, all right? Set them equal to 0, you solve. We skip a bunch of these steps, okay? If you want to look at all the steps, you can look at the textbook. They're all in there, okay? And we'll get we'll get these answers here, okay? Or okay. Now, one thing, all right, is you have to deal with these sums, okay? And this is, it's obnoxious, I guess, all right? A lot of times we have to deal with sums and there's not much we can do about it. But one thing where we don't, part of dealing with the sums, the summation is intrinsic to the computations is in linear algebra, right? So we've got a bunch of multiple observations. We have summation terms in the loss function, summation terms in the derivatives. And basically, if we switch to using matrices, then the summation is implicit in matrix multiplication, right? Because if you have a vector and a column, and you multiply, you do matrix multiply between them, you're doing the element-wise multiplication, and then you're adding them all up, right? Kind of your cross product. So that operation takes into account the summation, all right? So we can get rid of these summation signs, and you took what, 33A, and it might have been a little while since you took linear algebra. I highly recommend watching this playlist and just subscribing to this channel, right? Like, comment, and subscribe on YouTube to 3 Blue 1 Brown. This playlist, it's like just watch it once a year, okay? Watch this playlist, okay? It should be like this, this is it's the author of these videos, Grant, has done truly an excellent job, and I don't know if you guys already are subscribed to 3 Blue 1 Brown. Okay, you already should be, but just watch these. Everything's really good, especially matrix chapter 4 on matrix multiplication, all of these things. Okay, it's all right. Anyway, I'll stop evangelizing on 3 Blue 1 Brown, but you should watch that. Okay, and so we'll approach this the same kind of idea, but rather than doing partial derivatives, we'll do it. We'll do matrix notation, vector-based derivatives and stuff. Let me go ahead and give you your second view quiz answer for today, which is the letter A. A as in apple. A as in apple is your second view quiz answer. All right, so we're going to define a few, matrices. So I've got matrix boldface W, and this consists of the two parameters W0, W1. So W will have, this is the vector W, column matrix, W0, W1 for the intercept and the slope. And one observation, if we're talking about one observation, it's going to be a column or a column matrix with a 1 and an x sub n, right? And you might wonder, like, why do I need to have the 1? Okay, well, if we have the 1, we can include the intercept term, because I can take, say, W times xn. I can multiply these two together. I can do W transpose, right? So W transpose times xn, and basically the W0 multiplies by the 1, and the W1 multiplies by the xn, and thus our linear regression equation, which is basically the intercept plus the slope times x, can be expressed as this single matrix operation of W transpose x sub n. All right, is that okay? So this is how we're going to do it, and this is why we need to include a 1 when we're talking about each observation x sub n. Okay, and so if I have all of my data is going to be big matrix, big X, capital B, no, capital, what, bold, I don't know how to say this. Bold letter capital X representing my X matrix, okay? This is going to be a column of 1s and a column of our X values, okay? Column of 1s and a column of our X values. X1 transpose, X2 transpose, going down to X sub n transpose. So we have capital N observations. And then our target values will be, the column of the actual values. And so the loss function is going to be 1 over n t minus xw transpose t minus xw. And so let me just kind of show you how this expands out, right? So if I just take capital X W, right? So here's my matrix X, column of ones and the column of all the X values, and I matrix multiply by the, what is this? My W matrix, the intercept and the slope, okay? So then this will become, right? So this is n by 2, and this is 2 by 1. N by 2 times 2 by 1 becomes an n by 1 matrix, okay? And it's going to be just all of the predicted values. It's basically what you get when you plug it into your prediction line. You have the intercept plus the slope times x, okay? And it's going to be this for every single observation in there, okay? Now, this is very important, is when you're doing this by hand, make sure, don't just write x and w and x, okay? Because when you do matrix multiplication, your dimensions have to line up, right? The number of columns in kind of this element has to match the number of rows in the next element when you do the matrix multiplication. And so always write the dimensions underneath these things, and you'll know whether you are doing your matrix multiplication correctly or not. So if you do xw, then x is n by 2 and w is 2 by 1, and you can say, okay, these inner dimensions, the 2 and the 2 match, and therefore I can multiply them and we'll get an n by 1. If you had swapped them, and if you try to do wx, you would have a 2 by 1 multiplied by an n by 2, and it's just not going to work, okay? And when you try to do something like this in R, you're going to get, what's the message you get? It's something along the lines of incompatible dimensions, okay? Basically, it'll tell you that you can't multiply these things together, right? All right, so okay, this is what I'm going to do. So in R, I'm going to extract the year as x, okay? How many observations do I have? I've got 28 of these things, capital N. I'm going to create a column of ones, okay? Or basically a vector of ones, repeat 1 n times. And I'm going to column bind the ones along with x. And this is going to be my matrix capital X. So capital X is 28 by 2. That's basically this thing, a column of ones and a column of the x values. 28 by 2. And then initially I'm going to just start off with my slope, or my intercept being 1 and my slope being 1. Okay? Intercept and slope will just be 1, 1, and I have a 2 by 1 column matrix. Okay? And so here I can do x times w, and the result will be 28 by 1. Okay? But if I try to do w by x, I get the error, non-conformable arguments. Okay? Non-conformable arguments. All right, and so if you encounter this while you're doing stuff in R, in matrix notation, it means your dimensions don't align properly, and a lot of times you can solve this by just going back and writing your dimensions out by hand underneath. Okay, so this is the column. So this is just an n by 1 column here, and what I can do is I can just take those values. These are the predictions, which is represented by xw, are these predictions, w0 plus w1 x1. And I can say each residual is going to be the difference between the target minus its prediction. So this is going to be t minus xw, right? T, and when you do subtraction or addition, it's element-wise. So t is an n by 1 matrix, and I'm going to subtract off xw, which is also an n by 1 matrix, and so the result is also going to be n by 1. Okay, so these, as complicated as this is just one column of values, all right? And it's all the residuals. The actual values minus the prediction. The prediction is found by doing xw, right? So far, so good? Okay, and therefore, when we talk about the sum of squared errors, right? I'm doing t minus w0 plus w1 xn squared, right? We could, if I expand this out, I could take each observation, t1 minus the prediction for observation 1, t2 minus the prediction for observation 2, so on, all the way to tn minus the prediction for observation n. So I have a row of n observations. I have a column of n observations. And if I matrix multiply this, which is basically t minus xw transpose, times t minus xw, which is this column, we can see that this is going to be t minus this observation gets multiplied by this observation is basically this thing squared, plus the second observation times this the second observation squared, plus the next observation, all the way until we get to the nth observation squared. And so therefore, this entire summation of squares can be just done with this, t minus xw transpose minus times t minus xw. Okay? And so this loss function can be, loss function with the summation, we can get rid of the summation by using matrix notation. We have 1 over n, which is a scalar value, times t minus xw transpose times t minus xw. So this is 1 by n times n by 1. And so when you multiply all of these things together, you're going to get a 1 by 1 value, which is just a scalar value, right? It's the same thing we would get if we went through and did every observation and we squared them and we add them up. We get a single value, which is what we want. Okay, we have a scalar value, and this is the scalar value we're trying to minimize. Okay, so what is this? What's happening here? Okay, well, let's expand this out, okay? We're going to do t minus xw transpose times t minus xw. And so I don't know if you remember all of your linear algebra rules, but the transpose of a summation or a difference is basically the elements transposed. And then the transpose of a product is going to be you flip the order, you reverse the order of the product, and you transpose each of those elements, okay? So when you do xw transpose, it becomes w transpose x transpose, okay? So here I've got t transpose minus w transpose x transpose times t minus xw. And then here you just kind of do your first, outer, inner, last, your FOIL operations as far as multiplication. So we do t transpose t, all right? And then again, just to kind of make sure everything is aligning, so t transpose is 1 by n times t, which is n by 1. And then we've got w transpose x transpose. We're going to do, the outer elements, the t transpose times the xw, okay? And this is fine. And then the inner elements, w transpose x transpose times t. And then we have the last, w transpose x transpose xw, okay? So we have this, all right? So this is, so each of these things are just 1 by 1s. If you look at the multiplication, we have a 1 by n times an n by 2 times a 2 by 1. That's going to be 1 by 1, and that's going to be 1 by 1, okay? So I've got t transpose t, t transpose xw, w transpose x transpose t, w transpose x transpose xw, okay? And these are all 1 by 1s. And I can add these two together. I can combine these two, okay, to get t transpose t minus 2w transpose x transpose t, w transpose x transpose xw, okay? Why was I able to combine these two elements? These two elements are transposes of each other, and they are scalars, right? So this is a 1 by 1 scalar, and so if you take a 1 by 1 scalar and you transpose it, you have the same exact value, all right? And so if you look at this, this is the transpose of this, because it's just in opposite order with transposes applied. Okay, so I can combine those things together, right? And so I can take this. This is the sum of squares up here, and then if I do 1 over n, this becomes our loss function. So this is the same thing as this, just expanded out. Okay, expanded out. Maybe simplified, I don't know. All right, so we have all of this. Okay, and now what we want to do is we want to find the value of w that will minimize this. Okay, and so we can do vector-based derivatives. Okay, a little bit of vector calculus. So we have our loss function defined in matrix notation, And we still want to go and find the value of the slope and intercept that are going to minimize the loss function. And so just like before, we're going to take the derivative, set the derivative equal to 0, and solve for w, except now we're going to do this in kind of vector calculus based. Okay? And I don't know if you guys have ever done something like this, but if not, that's okay. So if you think about derivatives, basically it's the limit of this thing, x plus a small value h, okay, minus f of x divided by that difference h, and you take the limit as h goes to 0, okay? And we can kind of rearrange these things to say that the derivative at f prime of x satisfies this, okay? In that if I were to kind of subtract f prime of x times h on both sides, this thing would go to 0, okay? So this is what we would get. And similarly, when you take derivatives with respect to a vector, you get something that we would call the gradient, okay? And so this time we have a function that maps from n-dimensional input values. In our case, we have 2 input values, slope and an intercept, and the function outputs to a single scalar value, basically the mean squared error. Okay, so we're going from 2 inputs, slope and an intercept, but the output is the mean squared error, and we're trying to minimize the mean squared error. And so we're going to take the gradient. This is this upside down triangle. This is called nabla. It's not, so the regular triangle is delta. The upside down triangle is nabla. Okay, who knows? All right, but and tells us how the function changes with respect to a vector. And basically, all I've done is I've changed all of these things from italic letters into bold letters to say that they're vectors, and we have to kind of put them into norm things to kind of turn them into scalars and stuff. Okay, but basically, if you have a function that outputs a scalar value, like the mean squared error, or the loss value, or something, whatever it is, when you take the gradient, or basically the derivative with respect to a vector, okay, so the gradient of the function f with respect to the vector w is pretty much a vector of the partial derivatives. Okay, so if you have multiple elements in w, or in our case we have 2 elements in w, a slope and an intercept, you basically get a vector with the partial derivative with respect to the slope and a partial derivative with respect to a vector is basically what you're going to get. Okay, the derivative represents kind of the slope of the tangent line. The gradient represents the slope of the tangent of the graph of the function, and the gradient is going to point in the direction of the greatest rate of increase, and its magnitude is the slope of the graph in that direction. This is kind of a handy little guide for getting gradients. Okay, so if you have some function, the function has to output a scalar value, a 1-by-1 scalar value, and if you take the gradient with respect to a vector w, in our case our vector w is 2-by-1, okay, the gradient will always have the same dimensions as the vector w. So if w is 2-by-1, the gradient of f with respect to w is going to be 2-by-1. So if we have w transpose x, which is 1-by-1, the gradient of this thing with respect to w is going to be 2-by-1. If you have x transpose w, the gradient with respect to w is also going to be x, which is 2-by-1. Okay, w transpose w, the gradient of that, this is 1-by-1, is going to be 2w. And then w, it's kind of like w squared, right? When you take the derivative of x squared is 2x, basically. It's kind of like that, okay? And then here, if you have w transpose c, w, where c is a square matrix with dimensions that align properly. So here, w transpose is 1/2, c is 2/2, and w is 2/1. The gradient of that is going to be 2 times c, c being a 2/2, and w, which is 2/1, and the result here is also going to be 2/1. And with them things. Okay, So let's go ahead and do the gradient of this with respect to W. So here's our loss function. And I've just distributed the 1 over n through all of the elements. Okay, so from earlier we said when we expanded out the loss function in matrix notation, I've got, I distributed the 1 over n here, and then we're going to, each of these elements are 1 by 1, and we're going to take the derivative of this with respect to W, okay? So this is a scalar value, t transpose t. It has no W term in it, so it's going to just be a zero vector, a 2 by 1 0 vector. This is W transpose this, and so this is going to be, with respect to W, you're going to just get, take out the W, you get X transpose T over here. And then right here, you have W transpose X W, all right? So treating this as matrix C, okay, X transpose X being a 2 by 2 matrix, we're going to get 2 X transpose X W, right? And so now I got negative 2 over N X transpose T plus 2 over N X transpose X W. It's kind of a lot, but does this feel okay, kind of? Maybe? I hope? All right. Take some time to review your notes here, okay? All right, what we're going to do is we're going to take this gradient, set it equal to 0, and solve for the W so that this solution works, okay? So here I have this equal to 0. I'm going to add X transpose 2 over N X transpose T to both sides, and then I'm going to just multiply both sides by N over 2 to kind of eliminate the scalar value there. So I have X transpose T is equal to X transpose X W. Solving for W, how do you get rid of something being multiplied? In linear algebra, there's no division by matrices. You can't divide by a matrix. But over here, we have a square matrix. We can multiply by its inverse, right? And then when you multiply things, you kind of bring them to the front. So we're going to multiply both sides by the inverse of X transpose X, X transpose X inverse. So this assumes that an inverse of X transpose X exists, and that's going to work as long as there's no collinearity, right? So as long as you don't have this singular matrix thing situation. So I can multiply both sides by the inverse of X transpose X, and we're going to get X transpose X inverse, X transpose T. Have you seen this before? X transpose X inverse, X transpose T? I don't know where you guys see it. 100B? 100C?
Yeah.
Okay. Somewhere along the way, you see this. Okay, and so, no, maybe, all right. Well, anyway, the solution, the matrix form solution of the parameters that will optimize you figure out your best slope and intercept is going to be X transpose X inverse, X transpose T, okay? And so, again, just to recap what we've done is we said, hey, we have a function that we want to minimize. It's the sum of squares residuals, or the mean squared error, okay? We want to minimize this thing, and we're going to minimize it by adjusting the slope and the intercept. We're treating the data that's coming in as fixed, okay? The x values that come in, the actual target values are fixed. We're going to adjust the slope and the intercept. We have these knobs that we can kind of turn, and we're trying to find the right combination that minimizes the mean squared error, the sum of squares residuals there. What am I doing? Okay, and then we just took some time to do it in matrix notation because we're going to be dealing with the matrices a lot. Okay, and so basically this is the summary, the result. The estimate of W that minimizes the loss function is going to be X transpose X inverse, X transpose T, and we will we'll continue to discuss this in our next lecture, which, again, reminder, let me give you your last quiz answer. Today's last view quiz answer is A as in apple. A as in apple is your last view quiz answer for today. And the next lecture will be tomorrow, 9:30 a.m. on Zoom. Use the same Zoom link as office hours, and I'll be there. And then no class on Friday, okay? So have a good rest of your day, and maybe we'll see you tomorrow on Zoom.